Okay. Welcome everybody in this workshop, which is organized by the Cluster of Artificial Intelligence Project.
John, we lost the audio. John, we lost you. So also the video image is frozen. Okay, just 1 minute to allow John to fix his video.
Or maybe, Paolo, you could do the introduction to the workshop.
Yeah. So, John, okay, John is here again.
Okay.
Yeah, I apologize for this. I think after 2 years with a lot of workshops, it's the first time it happened to me during the pandemic. My computer crashed. So I'm back. I was just saying that we are the cluster of artificial intelligence projects in manufacturing. We collaborate in different topics, ranging from explainable and trusted artificial intelligence in manufacturing to human-robot collaboration. As part of this collaboration, we organize a series of webinars and workshops. We had already our first 2 workshops in late 2021, one on explainable artificial intelligence and another on the legal issues. So today we are discussing about human-robot collaboration and human-centric manufacturing in the Industry 5.0 era. So these are topics that fall in the realm of Industry 5.0. So the human-centered aspects of manufacturing. We have 4 projects represented today from our cluster: Project Knowledge, Assistant, Teaming AI, and also STAR. And without further ado, we have excellent speakers from all these 4 projects. I would like to give the floor back to you, Paolo, just to explain some rules, and then to Stefan Walter from VTT and Knowledge Project for the first presentation. And for all speakers, feel free to introduce yourselves properly, introduce your project, and take your time to give the presentation. Thank you very much for contributing to today's workshop, and thanks for everybody being connected and attending this workshop. And once again, apologies for the connection problem before.
Thanks, John. Just a few words on the organization. Of course, the event is recorded, as John said, so that we can share the event with all that could not participate. Let me also say that during the speech, I will deactivate the mic for everybody. If you want to make questions, you can use the chat, and normally we have all the questions at the end of the presentation so that the speaker can organize the presentation in a faster way, more consistent for everybody. So having said that, welcome again, and I leave the floor to the first speaker. Or John, I don't know if you want to say another word.
No, Stefan, the floor is yours. Feel free to introduce yourself and your project. Thank you very much.
Right, thank you. Yes, so yes, first, thank you for the organizers to have this workshop. And in fact,
Yeah, not hearing you.
Stefan, sorry, Stefan, you have to activate your audio.
Sorry.
My fault.
I had it. It jumped back, I think. I actually thought I had pressed
apologies.
it. All right, thank you. So yeah, so my name is Stefan Walter. I'm from VTT Finland and the coordinator of Knowledge Project. Let me share the screen. Obviously, that makes it a lot easier. I hope you can see the screen.
We can see.
All right, fully wonderful. Yes, I was going to say in the beginning, thank you for organizing it and also for the organizing the entire series of workshops in this cluster. It's a wonderful opportunity, of course. So Knowledge Project is one of those projects in this AI manufacturing cluster that has started January 2021, and it's scheduled for 3 years, and it's going to finish end of next year. And we are focusing on developing a platform, basically an entire architecture. However, our main emphasis is artificial intelligence solutions, and here in particular solutions that are meant to be have various features, such as being agile, being standardized, collaborative, reusable, and yeah, and this yeah, so this presentation deals now with Industry 5.0 aspects, and I have basically used a kind of tentative title because it was a bit unclear how it's going to develop or what I'm going to put in there. So I'm going to cover some basic aspects of Industry 5.0. This is possibly what everyone maybe has, but it's still useful because we may have different understandings of what Industry 5.0 includes, even though we are focusing here on human aspects, human-centered aspects. Then I was going to talk about how human centrism exhibits itself in our project, and some implications, particularly, as I mentioned in the subtitle, management and resilience aspects, maybe also some related concepts, because Industry 5.0 is not the only one that deals with aspects of human centrism and related issues, and then some conclusion. So I was going to refer here to this report towards a sustainable, human-centric and resilient European industry. There is, of course, a ton of literature on Industry 5.0, but maybe just this might just be interesting because it's a kind of policy brief from the European Commission, and basically this is how they understand the issue of Industry 5.0. And this is, of course, relevant in connection to the various projects that we are involved in. So in this context, Industry 5.0 is about recognizing the power of industry to achieve societal goals beyond jobs and growth to become a resilient provider of prosperity, and then also recognizing the boundaries of the planet and placing well-being of the workers at the center. So it's this people, planet, and profit almost, but then instead of profit, it's about resilient prosperity. And another element here taken from this report is this, this kind of image, which is a bit like this triple bottom line idea of sustainability, where we are meant to integrate economic, ecological, and social aspects. And this year is about human-centered aspects, sustainability, and resilience. So human-centered approach, of course, deliberately places human needs and interests at the center of the production process. So it's not meant to be only in order to increase economic efficiency, but have this idea that technology should adapt to the process and the needs of the user. And then sustainability is maybe pretty much commonplace nowadays, but that's meant to be using resources in such a way that the resources are not exhausted and wouldn't compromise the needs of future generations. Of course, many of our projects have included aspects of sustainability, although this is not what I'm focusing on today, but we all basically are in some way or another concerned with making processes more efficient. And the resilience concept that has lately, on the last 2 years at least, experienced enormous growth in attention because of the COVID experience, even though it is actually a relatively old concept. It has been used in biology a long time, but here it is about the idea to make structures robust enough so that they are not breaking apart under disturbances, and whether this is COVID or any kind of other disaster or armed conflict. It's going to be important in the long run to make sure that any production infrastructure can be maintained. Now, if we look at the knowledge project itself, so knowledge I explained already. It has this. It's about architecture that has as its main focus the artificial intelligence solutions. We are 12 partners from 7 countries, and this picture here focuses on the knowledge innovative response. It's building up on characteristics of Industry 4.0, recognizing that companies have to reinvent their products, processes, and services, and so forth. But then if you look at the top of this pyramid, we see all these goals that we actually are aiming for, such as agile manufacturing and collaborative value networks, sustainable factories, and human AI collaboration. So they actually all contain already the elements that I mentioned before, which are meant to define Industry 5.0. And we can also see that there's various technologies and enablers. They include employee empowerment. They include various technologies that are meant to be combined. And then the outcome of this effort, we could very well call the technical or technological enabler of Industry X. And I deliberately call it here Industry X.0, because whether it's 4 or 5 is maybe not so much dependent on the technology, but rather on the setting, and maybe also about the, let's say, the willingness of an organization to transition from 4 to 5. But just to delve a bit deeper into the knowledge project itself, how do we reflect these aspects of human centeredness in particular? This is the knowledge vision, in which we basically describe the strategic and operational orientation. So we clearly are interested in supporting humans to make better business decisions, get business insights, obviously, but improve the way humans use and interact with AI systems, also to easily adopt new AI-based solutions. And then we have various challenges defined, which I'm not going to go into, but just that one, it includes human-centric design and human-computer interaction domain, where the architecture will keep humans in the center by developing suitable interfaces, and that should retrain and upskill the role of humans. So it's not only a kind of thing that is meant to allow humans to learn from, but also we want AI systems to actually learn from humans. So it's this kind of mutual improvement. Then looking at the architecture a bit more, that's not meant to be a comprehensive overview now, but this is the architecture. You can't see everything in the detail. I presume it's too small, but I'm just focusing on this one aspect here. So the architecture covers various functions, which we've called here layers, knowledge management layer, AI and data analytics layer, and so forth. I'm focusing on the one on the top, that is marked red, the smart decision-making layer. And that has the three elements that include the human-in-the-loop aspects of the platform, of the project. So this includes the specific possibility to incorporate human knowledge, to reason with data, to get results from user interfaces and dashboards, and to use insights and to get insights through digital twins. And then if we go a bit deeper here, a bit more detailed, so you see these three components that are part of this layer. One is the human AI collaboration and domain knowledge fusion. And that really allows domain experts to have their knowledge injected or to have their knowledge captured, their experience, so to speak. It helps, of course, to understand also what is happening better. So it's not just a black box, it's this explainable AI aspect. Then we have this decision support system component, mainly responsible for the dashboards and the interfaces, and that should allow users with little or no machine learning knowledge to interact with AI models. So this is, of course, also an important part. One doesn't have to be an expert to use these systems. Then digital twin, that is probably the most obvious to most, the digital counterpart representation of any given physical object here, whether it's an artifact or maybe a process. And then, yeah, how are we applying this? I didn't intend to go now into all these details here, but more to give you an idea of the various use cases that we have been having here. So the next three slides are very detailed, but really just for you to understand, these are the different kinds of use cases. So the first one's continuous tracking and data analysis of food parameters for process quality management. And second is fault detection and prediction for increased production quality and process efficiency. They are related to the same setting, the same pilot partner, and are concerned with production planning, scheduling, monitoring. Then we have here production optimization for small batch. This concerns fuel tank manufacturing in the automotive industry, consists of preparation of the process and the actual production process. Then we have AI video analysis, assembly supervisor. This concerns the automatic or the artificial intelligence monitoring of largely manual assembly process of gearboxes in the machine industry. So what they have in common basically is that we have all divided them into basically preparation processes or scheduling processes, and then in the second step, the actual production, either monitoring or interfering. And actually that's also what they all allow. So the first thing is what the knowledge platform allows is first you have comprehensive monitoring, status information, whether this is available resources, whether this is the status of the production line, the status of available tools or documentation in the workplace, very comprehensive monitoring of that. And then you have in the second part, you have this possibility to interfere in the actual production process. So where it becomes interesting for us here when we talk about human-centered manufacturing is the issue, what happens if there is a deviation in any kind of process. Of course, the AI purpose is to automate as much as possible, but not beyond that, where the AI is unlikely to produce better results. Or let's say yeah, where it's unlikely to produce better results, where we know that the human operator can actually produce a better outcome, and at the same time has the possibility to actually exhibit human empowerment. And what we do here is, when we deviate, the system basically prompts and says, please user, please operator, there is something not quite all right. Please check that for us, for me, for the system. And basically the operator is then, on the basis of their knowledge, adjusting it, confirming it, and then basically that solution which the operator has put in is then stored, documented, and then provided for future use as a possible solution in the future. And this is basically how the AI models learn from user input. Now, this might be at this point still simplistic, and we are also in this stage where this isn't actually realized. We have it conceptually developed in the architecture, but we are currently in that process of implementing the solutions. And I think this is actually something where we are going to have very interesting solutions in the future, where we have probably a lot of research that is going to focus on various methods to capture knowledge and experience in different contexts. So just to summarize this, still what I actually said. So we do understand that the human user experience and the way the knowledge architecture runs vis-a-vis human users, that this is really a central part of the system requirements. So while the demonstrators, they focus primarily on decision support, there is also many features which allow users to interfere. And then summarized here as understanding and learning about the process. I said we want to enable users and operators to learn. That concerns status and deviations about what is going on. Then analyzing data to plan the process. That's about interpretation. Storing and retrieving data, documentation, and then reason with the model in question, such as accept or adjust or inject or augment knowledge to the model as domain expert. So therefore, knowledge provides a significant feedback to the user, user-centered design, and both of them is about creating an explainable AI system. Then, of course, the actual impact, or the most important impact from the process, from this perspective of the actual manufacturing process, is that we improve the process and the product quality. So I said the situation is that we are implementing. That means we don't actually have real results in terms of what's going to be the actual implications or impacts. And here I have chosen two more speculative elements. The first concerns management. If you think how management is actually done in companies, usually you see the top-down aspects. The top, there's the top-level management giving direction to the lower levels, and that is forwarded to the operational level, the execution level. And in reverse, you have then this bottom-up approach in the middle, which is a bit more like a theoretical one. I don't know if this really exists in practice, but just for analytical purposes. And then you have the combination of both in the circular approach, where a company might set framework goals, but then things are actually planned, integrated, implemented bottom-up. And I think that this is something that generally leads to a strong participation and acceptance, motivation on the part of employees. And I think that AI, as we have described it, with this human empowerment aspects, I think that this triggers this kind of participatory management. So even if you have a company in which which is governed in a very sort of classical style, top-down, if they adopt AI solutions, then they will probably move into this more circular approach, simply because it's just the practical way of doing it. If you know that employees can make decisions, then eventually they will start making decisions, and it will then become the task of the actual management to more coordinate and integrate what has been done, but not anymore to necessarily plan everything. And I think this might also increase still the demand for AI, for planning and decision support, first for management itself, and then maybe also for to actually enable workers to be in the position of being empowered. Because the idea, of course, of human-centeredness and human empowerment is a great one as such, but then if workers aren't actually capable of making a decision in a certain context, then it's a problem. And AI, of course, can also provide important insights to make that sure. Then the other implication, resilience, we mentioned it already. How does a system organization deal with perturbations, disruptions, unexpected events? So the idea here is that this is a concept that goes beyond traditional engineering questions. So it's not just about trying to engineer, trying to just reorganize so that the organization, the company is going to be more resilient. I suggest here that it is a more dynamic process that includes human agency for learning, for leadership, for addressing uncertainty, challenges. And the idea is that what you can see in this supply chain model here that I have drawn, if you think that at the right nodes, you have employees who are autonomous because of the AI interaction capabilities here, then they can make decisions in events which any kind of top-down planning would not be capable of. Right? In all sorts of unexpected events, they are able to respond in a much more flexible way. So with these kind of solutions, you will have more resilient structures in connection with the mentioned management changes. So what this requires is organization and technical infrastructure such as architecture that's agile, flexible, open, and so forth, like the knowledge architecture, which does exactly that. And then the second part is then you need a suitable organizational culture. And I said before that I'm thinking that with the increasing use of AI, we will have a move towards this more human empowered management style. Yes, then still some references to related concepts. I just think that while Industry 5 is of course a very powerful one, and that's particularly known because of Industry 4, I presume, there is still other concepts which have incorporated similar features, which also provide comparable approach to transition. In this case here, Sustainable Industry X, Cognitive Manufacturing Vision, developed by VTT already 2 years ago. It is arguably more use case oriented, focusing on renewal of production, open manufacturing networks and supply chains, and this idea from products to services thinking. But otherwise, it has incorporated similar features, describes it differently. Then another concept that is a bit more, maybe less known, I presume it's less known, Decentralized Technical Intelligence, short DTI. That's being worked out in a working group on decentralized technical intelligence for increased manufacturing performance under the ManuFuture organization. And it also has a transitional focus However, using a systemic and interdisciplinary approach, so considering other than just engineering, it has a arguably more technical, let's say, inclination. But it's anyway about system optimization pathways meant to be autonomously close to manufacturing processes on the edge. So that's a white paper that is not yet published, but it should come out in the near future. And this will be followed by a roadmap for implementation in the industry. So that's also something to pay attention to. It is anyway, it will have similar impacts, I believe, as Industry 5. Then just a couple of points in conclusion. Yeah, so we basically understand that problems facing society, that is the whole point of Industry 5 in a way, can no longer be solved from the standpoint of one discipline, in this case, engineering or computer science. So therefore, we have these approaches which allow us to broaden our focus. And yeah, what I think is that these ideas that define Industry 5, such as human-centeredness, sustainability, and resilience, they are in the air, so to speak. And this is why we find other approaches too that might represent processes of the future in a more interdisciplinary way. One issue, of course, is that not all goals that are defined here can, of course, always be made compatible with economic efficiency. And this is, of course, always a kind of source for conflict, probably, because in the end, making people more autonomous, yes, it is great. If it's, you can easily argue you want to have more resilient structures, but they cost more, usually. And so it might not be always efficient, or it might not be always compatible with this idea of economic efficiency. Depends on what the organization wants. So it can be a conflict, but maybe it's also a possibility for AI to play a role in the future in balancing these needs. This is something that is probably still going to gain in importance. Okay. That is the end of my presentation. Thank you very much.
Thank you, Stefan. We have some questions from the chat. Maybe, Michael, you would like to ask them, right? I would say more the technical questions, because what is Industry 4.0 and Industry 5.0? For me, it's a very philosophical thing as well, at least from the events I've attended during the last year, right? From the Industrial Internet of Things World and the Hanover Messe till workshops like this, there are different viewpoints, but I think we will all be glad to hear your questions. So please feel free to just ask them instead of me reading the chat.
Thank you for that. Generally, it was interesting presentation. Sorry for me to join so late, but I have to implement Industry 5.0 already in another factory at the moment. So my question was, because a lot of things which you mentioned generally related to AI and are connected in my eyes, including digital twins, to Industry 4.0. Where was the turn that you start to consider it's not 4, but 5.0, because, as a founder of Industry 5.0, I have defined it in 2015 already. And it's not only about the waste, the physical one, it's social, urban, and process waste. And this is why, this is the part which I am generally missing, but maybe it is there, I don't see it. So what was the point when you start to consider, okay, it's not 4, but it's 5?
You mean that, of course, now specifically in our project, perhaps. Well, let's say our rationale is actually 4.0. What connects to 5 is actually more speculative. Let's put it this way. We do see these various goals, and I think they are pretty much compatible with various definitions of 5. And that was where I would say that, yes, of course, we touch upon 5, most definitely. but it wasn't the original rationale in starting this project. That is an important aspect, perhaps.
I see it exactly so, because as you mentioned, it was already delivered, and I see artificial intelligence within Industry 5.0. That's correct. I just see its application slightly different. But this is about the discussion, how it can be applied and so on. So very important. Thank you for the answer. It's clear all what I need to know. I will have a lot of questions, but we can get in touch on LinkedIn and so on, and not to disturb the event itself. So thanks a lot. And
yes, thank you.
I will stay tuned for sure.
One point here before we go to the next presentation, Michael, this is John. What is, the definition, or what is, let's say, the paper where, is the source of really defining 5.0 and the boundary to 4.0? Because, for example, the paper of the Commission and also, papers from various consulting firms in the industrial Internet of Things. I'm not going to say names, but you understand what I mean. They are not very insightful in this respect. So in my opinion, the boundary between 4.0 and 5.0 is not very clear, right? It's blurred at all these papers. But if you've got any reading that we can, consult to make this boundary clear, I think this is a helpful resource for our community. So please share it.
Thank you for this. Generally, the very original article was published on December 1st, 2015, and it's called Industry 5.0 from Virtual to Physical. Which is a very different direction than Industry 4.0 is going. And then 2 years later, there was a definition, Industry 5.0 definition published on February 3rd, 2017. The difference between these two is very simple. Industry 4.0 aim more production, more volumes, bigger quantities. It's generally an economical tool. And as it was developed by Siemens and introduced by Siemens in 2011, officially in 2013. But Industry 5.0 aim very different thing. It aims the construction of wasteless world in a meaning of waste, physical, social, urban, and process waste. And if you take all these four wastes together, then you have life. And this is the difference, because it's not about economical tool. It was not developed open and order from a government like Society 5.0 in Japan, for example. No, it was really, I am for 30 years in logistics, for 30 years in a business. I started as a steel factory, I work, just one answer, there is no academic paper because I am not academic. But there are 3,000 articles about, and many academics already refer to my work. So as United Nations, so as European Commission refer to my definition. But I am not academic, so these are not official papers.
Well, it doesn't have to be academic, right? The Bitcoin paper, changed the world, and it's not academic, so it doesn't have to be academic, right? It doesn't have to be. What I'm saying here is, Michael, and I think you will understand my point here is that sustainable manufacturing, reduction of waste, this is also part of 4.0 in many works. Maybe not in a holistic way, if you put it this way, but reduction of the different types of wastes, whatever the World Manufacturing Forum defines waste this is part of a lot of 4.0 works. And even mass customization and mass personalization, these are also part of 4.0 work that some people reintroduce it. Anyway, I think we can go to the next talk. Feel free, if you want to share with us a pointer in the chat. I think it's going to be very helpful for our community, really, I believe. Although, we have academics here, but we cite academics and non-academics. Okay. Yeah. I don't know if there is no more points. I think we can move on to the, thank you, Stefan, so much. And we can move to Christos. Feel free to introduce yourself, your project, and the presentation.
Okay, hello everyone. I'm Christos Gkournelos. Can you see my screen?
Yes, yes, Christos, go ahead.
Yes.
Okay, thank you. So, hello, I'm Christos. I'm a research engineer in Laboratory for Manufacturing Systems and Automation, or in short and form LMS. And I will present our work in Assistant project, working in the loop framework, enabling human-robot collaborative assembly. Assistant project target is to enable the use of AI for decision making in all sort of manufacturing levels, from the highest level of process planning and production scheduling to the lowest level of the execution control. Our contribution as LMS in Assistant, it's mostly focusing in the different objectives related to real-time actuation on the lowest level, and how we are putting the human at the core of the assembly system. To begin with, I would like to give a quick introduction to our research group that I'm coming from. LMS is oriented on research and development in cutting-edge scientific fields of manufacturing. We are located in Patras, which is in the west side of Greece, and we are part of the Mechanical Engineering and Aeronautics Department in University of Patras. Robots, Automation and Virtual Reality in Manufacturing Group is focusing in advanced industrial robotic application, which include the cooperation of multiple resources and multiple machines, the human-robot interaction with augmented reality and virtual reality, and in general, the human ergonomics analysis and modeling towards future and advanced industrial applications. Okay, so now moving on to today's presentation, I would like to start from the industrial challenge and the motivation that we have for our work here. So the motivation, it is worth starting from the fact that in recent decades, consumers are asking for more and more goods accepted to their personal needs and performances, as the Industry 4.0 paradigm framework has already observed. So next, what has been observed is that the various commodity industries are having difficult meeting the ever-changing market demands. So in Europe, we often encounter two types of production system. The first type includes automated production lines, in which the level of automation reaches up to almost 100%. And in this kind of systems, it's very efficient, and mainly in mass production, these systems are operating quite well. However, the processes are predetermined, the robot and the machines are fixed and pre-programmed, and the cost and the effort to introduce new variants, it's quite high. So the second category, in the second category, we have the systems that rely mostly on people to carry all the production processes. These systems are found in industries with a high degree of product personalization. And here we have the flexibility that it's needed to change. However, employees are repeated repeat painful processes and for long periods, so this accumulate a fatigue that it's a great problem. So, recognizing the characteristics of the aforementioned categorization, we see on the hand the human factor is necessary in production due to the ability of people to use their cognitive function to automatically respond to changes on unplanned events in production. as well as the ability to manage objects with complex and flexible geometries, which the behavior of this object is not easily to define. However, robots are capable of achieving greater accuracy in each process and are suitable for performing repetitive tasks and keeping their execution time constant. So the challenge and the challenge that we would like that arises here is to enable the work to collaborate, people and operators in a good fashion, and in order to utilize and to highlight the advantages of both. So towards this direction, human-robot collaboration began to take place during the Industry 4.0 era, and as depicted in this slide, we have a big variety of research that has already contributed in the creation of a human-robot collaborative system. So an operator is able to work together with an industrial robot and to have smart interfaces that will assist the operator to interact with the system and in overall to have an efficient collaboration. Despite the years of research, there are still limitations in the fulfillment of this idea. So it's not an already solution that you can find in every production, and we think that in this approach, AI system is still too distant from the human needs, and for this reason, we need to dive deeper and to see more closely all the individual applications of AI, how is constructed and how is framed. So, in Assistant project, we introduce the worker in the loop framework, which aims to align and coordinate the usage of several AI components for the realization of the flexible human-robot collaboration. The loop starts and ends with a worker, and starting from the inputs that we get from the people, from the workers, we have the sensors that are capturing data and consumed by the human body detection modules that are responsible for detecting the posture and the position of workers in the workspace. Then we are moving on to the human intention and task prediction in order to identify more closely what the worker is doing, and all these models an overall worker's behavior that is feeding into a digital twin that is responsible. It's the responsible component for creating the digital counterpart of the system. In this framework, it is quite essential to have a digital twin in order to maintain the connection of the operator and the rest of the system, which it is another robot or it is some other machines and an assembly execution controller. All the required information, such as the assembly instructions or the behavior of the robot, is captured is retrieved from the digital twin, and in order to be published to an operator, the usage of smart interfaces is required to close to finally close the loop. Now, taking a more close look on each component that we presented in the previous framework, we should start on the crucial aspect of safe human-robot coexistence. So, without ensuring always the safety, the safety of the operators, the previous framework will be useless. The existing safety standards are constantly updating in order to include more and more technological advancements that always ensure safety, but also includes new sensors and new software toolkits that improves also the system's flexibility. Human body detection, it is responsible to provide in real time the required information of the human position and the whole human skeleton to the robot planner in order to avoid collisions at the collaborative and at the shared task execution. Now, in order, as we fulfill the safety, in order to establish a proper and a good collaboration between robots and humans in a seamless way, not in a strict collaboration with with many buttons to be pressed and to have a very fine program. It is required from the system to understand implicitly what the operator is doing. So towards this idea, human task prediction component comes to provide such information by getting the usage of multiple AI components that would understand at which process step the human is. So in order to inform and to make a shared task planning. Moreover, the system resilience could also be improved by avoiding possible faults that can be detected at the assembly execution. Now finally to the smart solutions for the efficient interaction. Here, the key challenge is to achieve the user acceptance. So together with all this advancement in the technological point of view and on the development of AI, we should always maintain the idea that all these tools should be ready to be used by simple people operating in industry, and for this we should provide simple and efficient tools in order to gain the most out of the workers. So towards this direction, multimodal interfaces are proposed, such as augmented reality headsets and wearable devices, tailored to each use case specification. So for any case, it could be different, but always we should have under our thinking that we should enable the easy interaction with the system and with various tools. Now, some points in conclusion. Human-robot interaction can become seamless with the tightening of AI in the interaction process. Improve production system performance by combining flexible mobile robots in cooperation with people. So this the whole performance of the production will be improved with this comparison. Increase responsiveness of the system through the digital twin-based replanning tools. Improve human operators' ergonomy by allocating different tasks to robots and different to human operators. Enhance always the safety by adjusting robots' behavior based on operators' intention. And finally, several advances still are required in planning and interaction AI for achieving safety in the system. So Industry 5.0 are, I don't know, it was a very nice discussion previously. It's I think in my perspective it's difficult to define the borders, but I think that for sure this tighten and this enhancement of AI in real application for sure is something that in Industry 5.0 should be addressed more precisely, and it's something that was missing from the previous era. that's all from my side. Thank you for your attention, and I will be happy to answer your questions. I think I was on time also.
Thank you, Christos. Are there any questions to Christos? I don't see anything in the chat.
May I ask yeah,
I see some question. Oh yeah, please go on, Michael. I see some question on the previous presentation. Maybe Stefan can have a look and answer later. But please, Michael, go on and ask any
Christos, just one question. I have seen similar systems already applied in factories because I am almost every day in a factory. But have you considered that the volumes can even drop to increase the profitability of the business? And have you considered how generally can your technology or system balance this, which means you don't need to produce more, be more profitable?
Yes, exactly. Actually, this is our target. Mass customization for sure. It's not will not be better with a human-robot collaboration. So, as you said, personalized products in lowest volumes could be the solution, could be more profitable, and through human-robot collaboration, this production will be more efficient, because currently there are yes, for sure there are still some cases, but for small businesses that usually have small volumes, this kind of technology, it's not ready and it's not easy to be used. So also this is another aspect that for sure we should work a lot on.
Thank you.
Can I just add a small note here because of Christos' very nice presentation and Michael's comments. I think there is no golden rule right now in the manufacturing sector because it varies from sector to sector. The results that the pharmaceutical manufacturing company wants to achieve versus a heavy manufacturing, let's say, metal industry or a yogurt industry vary. So we need to take account different elements of different sectors and try to find a rule for what the presenters have been discussing about.
Exactly.
Can I also ask something, have a question?
Yes, please.
Yes, hello, this is George from Athens Technology Center. I would like to ask Christos related to your presentation. You only take into account signals from sensors or sensors that are in the body of the worker, or do you also use cameras in the environment? For example, you had a nice image about collision detection and avoiding collision. In such cases, do you also use cameras, or in terms of this project, you only use sensors on body's worker, or you also use cameras and stuff like that?
Yes, actually, the idea here and the work starting to create a framework that it's open to establish all kind of architecture. So in assistant project, we are going to develop a multi-sensor system combining both stationary sensors, 2D and 3D vision cameras, and also some wearable sensors on the robot, on the operators. So it's open to use all the architectures that you want in terms of sensor acquisition.
I see. Okay, so it's like an open system that can integrate more than
exactly.
one. Okay,
exactly.
Thank you. Thank you. Very interesting.
Christos, one more question. I see in more and more factories, especially abroad, India and other countries, even in the US, I see a lot of companies are switching to not high-end, but generally low-end applications and technologies, which can be easily manipulated by the people. As I see in the open architecture, which you spoke about, you are really not limited to anything at the moment when we say it. So it must have some output and input, then you can apply it and you can use it. So, and you already implemented in some industrial environments, in some projects?
Yes, actually, in assistant project, we have 3 end users. We have Stellantis, the automotive manufacturer. We have Atlas Copco, and we have Siemens. So our framework will be implemented in these cases and will be tested in these cases. But as you very good mentioned, the hardware requirements should be always independent on the system. So because we should always provide technology to any kind of businesses, and as I said before, SMEs are not able to fund and to invest in such in a high, because currently human robot collaboration is considered as quite high investment. So the idea is to make it also costless and as cheap as possible, with low-end sensors, with existing robots in the production, in order to advance the existing automated application into a human robot application.
Why I'm asking and why I was not on my seat. This is generally one of the low-end solution which can be.
Yeah, actually, it's not very clear.
It's called IQ Hub, and the operator just turn the switch to the operation. I will send you a link after. It's not a problem. Show how low-end solution, and it really works in a factory because it's a heavy machinery factory, and the operator just has to indicate in which stage is the production. So he switch it like a clock, and it works. It sends several sensors. It's quite interesting. I was really surprised about the efficiency of similar technology, and I can imagine the application in environments. Of course, Siemens and the other big players which you mentioned has a lot of money to invest. But you mentioned the small SMEs. Similar solutions are very interesting for those because you implement the solution, just the tools are slightly different, but the results at the end is the same. So this is what I will call Industry 5.0. That's the touch. Maybe we reach the touch between 4 and 5. So great. Thanks.
Thank you very much.
Okay.
Okay.
Okay, thanks, Christos. I think
let's move to the next presentation, Teaming AI and Bernhard. Bernhard, yes?
Okay.
Thank you, Bernhard. Please feel free to introduce yourself and your project.
Okay, thank you very much. So, can you see my screen? Okay, yes. So welcome to my presentation, and thanks for organizing this interesting workshop. My name is Bernhard Moser. I'm coordinator of the ICT 38 project, Teaming AI, which is on human AI teaming, as the name is telling you. And here I want to for this workshop here, I want to pick out one special issue. It's about the dynamics. Okay, but I think some of the discussion I can make rather short, yeah, because there has been a lot of discussion about Industry 4.0 versus 5.0. But one issue is also from the market side. Okay, it is a quite recent a market study from Gartner telling you that this is really important and of high relevance. If you see at the revenues of digital workplaces, okay, and okay, now I will also was already cited by the knowledge presentation from VTT, this document from the European Commission about their strategy towards Industry 5.0. I want to go into details here. I also on here I just also cropped out some fragment in one table where they make a comparison. On the left hand side they have Industry 4.0 and on the right hand side 5.0, and this is one aspect, yeah, to empower workers through the whole digital through the use of digital devices, endorsing a human-centric approach to technology. Of course, this is a very high level, yeah. So, but in the end, what we want to concentrate, and what is a big challenge, was already also discussed and pointed out, is there is a conflicting, let's say, goals. On the one hand, we want to concentrate on ensuring ethical values and human values on the one hand, okay, and on the other hand, of course, we don't want to lose competitive edge in the global market. So how to bring this together? Yeah, it's a really big challenge. But, and this will be an argument that we need a human, also, or to integrate human intelligence, also for the reason for flexibility, and so in the end to achieve more performance for special applications, of course. So, and one reason for this are limiting factors of today's machine learning-based AI. So, by the way, what I'm talking about is compared to the last presentations, more in the middle. Okay, the knowledge was, I would say, more on the management aspects, so to say, more top-down. The last one, assistant, robots and so on, were low level. And I would say what we're doing here is more in the middle layer. So we are directly addressing related artificial intelligence topics, yeah, and there we have to take into account what are the limiting factors of today's AI systems, okay, and there are some limitations coming already from the theory, yeah, from the statistical learning. It's about okay, deep learning, where we have a totally different situation as in traditional engineering. For example, for such high dimensional and multi-parameter systems with often millions of parameters, we lose uniqueness of the configuration. Yeah, that's one problem. That's a problem with comparison and so on. So the other one is that there is no theory-based confidence of the outputs, and there are high dimensional effects, okay, which are not under control. For example, I'm sure you know about this adversarial attacks problems. This is due to some high dimensional effects. Then there is also the problem of how also the theory is one part, okay, and this is I would say quite restricted, but due to the big success of all these methods, more and more applications are tackled, which are beyond the border, so to say, of the theory, and there we have an adoption gap. Okay, so I mean this theory practice gap, okay, because what we still have is this narrow AI systems restricted to limited tasks or predefined tasks, which are quite data hungry, and in the end, in practice, the situation is that we don't have the full big data, which we would like to have for fulfilling the assumptions of the theory. We don't have them. We only have limited data, and with limited data, we have a couple of problems related to this. For example, the bias problems, selection bias, and other bias problems. And another problem is that explainable AI is not really fulfilling its promises, I would say. So with limited, all the limited functionalities. The problem is here that often in such applications, an application model is missing. But here humans come into play. So the other point is, that was already mentioned, is the adoption gap in industry, related to high costs in the initial phase. And of course, it is also very demanding from the point of view of the skills. And of course, this is what is also Industry 5.0 is about these social aspects, okay? So to mitigate acceptance problems and also to address skill gap. Okay, this is on the AI side, but of course there are also limiting factors from the human side, of course. I don't want to go into details here. Everybody is aware about this. Cognitive overload, also human making decision biases, and problems of out of the loop due to, for example, habituation effects. So, but in the end, so these are limitations, these are weaknesses, but of course there are also strengths of the AI systems, but also from the human side. Okay, and now it's about to talk about or to think about how to organize, how to orchestrate, and how to manage a collaboration, so to take benefit of both strengths. In here, this is from literature from publication from 2018. In the meanwhile, there are much more publications. But here, I think this illustrates very nicely the problem that there is some missing middle between humans and machines. Okay, much research and investments have been done in this direction of assisting humans, but on the other hand, and this is the point, there are so many limitations I pointed out from the AI side. So we need also human support to assist, to guide, and to interfere with the AI system. Okay, so, and there is an interesting study on the state of the art of human AI teaming from the National Academies of Sciences in the US from July 2021. And they outline key challenges and research gaps. Okay, and one of the major research gaps is about to address the dynamics in all this. And this is the focus, or one of the foci of our teaming AI. And now I want to go into some more details after presenting, so give you a sketch of our use cases, which are quite similar to what already have been shown by the other presentations, quite similar, okay? There are some, so here's some inspection problem for automotive industry. This is a little bit different. This is some machine diagnostics problem for injection molding, which is a quite complex process. Of course, it is about quality control and maintenance. And here is also quite similar what we have seen before, is about small batch production of quite heavy, big parts. And with this is also safety critical, and yeah, some assembly process here. So, and now I want to dig in the more artificial intelligence related questions. So teaming is a quite new aspect in the field of artificial intelligence, but not for humanity. So without teaming, we wouldn't exist as humanity, I would say. And so the first starting point is to look at social sciences, what they have to say about teaming. And teaming can be quite challenging, quite complex. So we have here different aspects of teaming or collaboration. Of course, roles, it's about skills, it's about independences, it's about processes, and also forms of also management forms, of course. So this here in the middle is a picture from this publication here. This is from Social Science. They're talking here about the big five of a teamwork. And there are some aspects like, of course, mutual trust, shared mental models, and so on, which are quite vaguely defined in this context. Yeah, and the problem is, at least for us, yeah, how to make some aspects of them operational and integrate them in an artificial intelligence-based system. So this is just one example where we, it's related to one of our use cases, where we do some independence analysis between the operators and the tools of the machine. Okay, so, and now one problem, or one big problem, as I pointed out, is dynamics. Yeah, but dynamics we have at different levels. So here, of course, there is at the top level, we have some static knowledge, which is managed by some offering a tool for modeling the process and also what we know about the application. Here the problem is also about to which a granularity level we can or we have to model it. On the other hand, there's the team model, also the skills, the roles, and so on. Of course, this is related also to the problems of human factors and about it also depends on, for example, the skills. Is it more experienced one or not? So, and then we have, this is situational awareness is a big issue here. And in the end, the human interaction, of course, related to a mental model, and how to this plays together with AI device decision making. So, and of course, the application in the end to some decisions and control some system. So in the end, so we have the process, we have the teaming process, and of course, at the top level, the knowledge model. And of course, this has to be, has to play together and updated, has to be updated all the time. And that's one of the problems. So this is our architecture. And we use the flexibility of knowledge graphs at all the levels. Here you see, so this is, sorry. So here you see at the top, at the bottom level, the production environment and some monitoring agent, here the human, and there, that's one major component is a dynamic knowledge graph, which manages this updating. Yeah. And now some words about the design of the knowledge graph. This is not that easy because of the complexity. You know, knowledge graphs from, for example, Facebook or so, yeah, which can be, or also in the industry. For zero, there's a knowledge graph. This can be quite large, quite complex, yeah. And the question is how to make this modular, how to make this comprehensive, how to make this processable in an easier way. So, in here, yeah, for example, one aspect is to use also some concepts in terms of abstract activities. This is from the Grammar project, which is in the EU project. Abstract activities differ from concrete activities in without saying, so to say, what are the resources to realize one concrete activity. So it's more abstract than a concrete activity. And yeah, and for the processes, by the way, we use a version of BPMN, yeah, with some extensions, for example, with respect to these abstract activities. So in the end, then we have some knowledge graph and some knowledge model. And now the problems comes in, yeah, how to maintain this. So because in the course of production, the course of application, and due to the situation awareness, there will come in new facts from loggings or whatever, right? Okay, and we have to update and maintain this knowledge model. So, and one problem with knowledge graphs, so the advantage is that it is quite flexible, but on the other hand, there are also some drawbacks. And the drawback is that the semantics is not that strict. So building up a knowledge graph can lead to incompleteness and inconsistencies. And that's the problem now, yeah, how to manage this. And this on the one hand, and on the other hand, so it's the knowledge graph model itself, but in the end, we want to use this knowledge graph to enable further machine learning, yeah, recommendations, for example. And this needs a component that carries this graph over into some form which can be computed by machine learning. Yeah, and this is about knowledge graph embeddings. So an embedding takes a graph here, yeah, and embeds this into some vector space. So so of course, in some special way, so that relations in the graph are somehow reflected. And then here, machine learning can be applied again. So, and the problem, what we have here with the graph itself, we also have for the embedding. So if we have some changes here, sorry, so the problem is that also the embedding would have to be computed again and again. Yeah, this is of course can be very, very time consuming. So there's one approach by one of our partners, that's University of Mannheim, Heiko Paulheim, and he and his team. This is about an approach that is able to predict inconsistencies and faulty entries or missing links. This is not that easy because if you would apply, for example, here it's a graph convolutional neural network, yeah, which is used here, but just applying this is not that successful because we get a single assignments to some of the entries, okay, with a softmax, for example, and this could lead to overconfidence. Yeah, what is done here is like in a consensus based regime. Yeah, think of a court, yeah, where various judges have different opinions, and then this is averaged. And in this way, this is working with some in some Bayesian framework, yeah, and which in the end is much more reliable and also interpretable. So here, with this approach, we overcome this problem of overconfident predictions. Another one approach is this not just about missing links, it is also about misconceptions in the whole knowledge graph. Yeah, it's about predicting instance types. And here we have a new method. It's called RIDLE, which is also about doing predictions of this. So I think I will not go into more detail here, but these are some low-dimensional projections of these clusters for inspecting how well they are able to separate the clusters. And so what you can see here in the top row, that with this new method, we get a better separability. These are very important, so that, and by the way, with such methods, we also get an uncertainty model, okay? For example, if the cluster is the clusters are very, very well separated, then the system can do the correction by itself in an automated way. If the clusters are not well separated, this is a hint that we need human intervention to resolve this. Okay, and there's and the other problem now, the second one, so these two methods I just outlined is for the knowledge graph itself, and this one here is about the embedding, yeah, because we also have to think how to make the updating of the graph embeddings fast. And this is a new method here, which is about reconstructing the embedding from the embeddings of its neighbors. Yeah, and so to say, it's a neural network approach. Yeah, which learns the to interpolate the embedding from its neighbors. And it's interesting that in at least, okay, this is still a work in progress, that in some cases, yeah, we see that, okay, one moment, yeah, okay, that in some cases, the accuracies and the performance is quite comparable. On the one hand, if we do this learning on the original embeddings, yeah, and then compare it to constructions with this method. So the here in this here we use some standard benchmark databases, and so these preliminary results here are quite promising, where you can see that the results are quite similar. Of course, this depends on how much corrupted, so to say, the knowledge model is. Okay, and with this, I want to end my presentation. So it was just one point which I picked out, but I think this is a major research need we have to tackle. Thank you very much.
Thank you.
Thank you very much. There are some questions in the chat, right? I think that for the human digital twin question, we can take also with the next presentations, because these are what are all about. And another question is whether artificial intelligence can be used to proactively avoid the waste. So maybe because we are a little bit falling behind schedule, we can have a quick feedback on this, Bernhard, and we can move to the final presentation by Elias and Jože.
Okay. The question is whether AI can predict. Okay, of course, but this depends about. Depends on the context model, yeah, and what information you take into account. Once, and this need not be perfect. So that's the point I want to say, yeah. So we have a machine learning system, a predictor, yeah, but this is not enough, I would say. It's not flexible enough, yeah. What we're doing is to enrich it, to augment it with some context model. This is this knowledge graph, yeah. And this has to be adopted and with the help of humans, okay. And so that's a starting point for doing. The more information we have the more complete it is in the knowledge graph. Of course, the better the machine learning system can make predictions, of course. But the question is how to make this operational, yeah. And often I have heard or read a lot about high-level conceptual stories about human AI teaming and so on. Okay, but how to realize this?
Okay, let's move to the final presentation, and in the end, so that we can have a discussion and
okay.
Questions.
Thank you.
Let me share. Do you hear me?
Yes, Elias, please feel free to share your presentation and introduce yourself and your project.
Are you able to see my screen?
Yes.
Okay, great. So greetings, everyone. My name is Elias Montini, and together with Jože, we are here on behalf of the STAR project. In this presentation, we are going to see some of the solutions that we are developing in the project towards the human digital twin and towards human-machine collaboration. So before starting, a brief introduction of ourselves. I'm a researcher at the University of Applied Science and Arts of Southern Switzerland and a PhD student at Politecnico di Milano. My research topics mainly deal with collaborative robotics, human-centered production systems, and also human digital twins. And in particular in STAR, with some colleagues from SUPSI, we are the leader of the work package dealing with the human-centered simulation and digital twins for safe and secure artificial intelligence. Jože, do you want to say something about yourself?
Yes, thanks. I'm Jože Rožanec. I am a PhD student at the Stefan Institute International Postgraduate School. I also work as a machine learning engineer at Collector. It is a company that tries to build this kind of smart products for manufacturing enterprises. And currently we are working and focusing only on active learning and explainable artificial intelligence so that we can build value on top of these approaches for manufacturing.
Thank you. So, okay, this is the outline. So first, a brief introduction of the project that we have an overview about what we call adaptive and mutualistic production systems and on human digital twins. Finally, then an infrastructure that we are realizing in the project STAR towards human digital twins. And then Jože we will provide some insights about active learning and explainable artificial intelligence in manufacturing. So the STAR project started in January 2021 and it involved 15 partners from 10 different countries with complementary expertise, like we have technology providers, manufacturing and users, research centers, and universities. The goal is to develop safe and trusted human-centric artificial intelligence technologies and to validate them in relevant industrial scenarios. STAR deals with the development of edge artificial intelligence technologies to be applied in manufacturing production systems. In particular, these technologies deals with explainable AI, active learning, human-centered digital twins, simulated reality, and security for artificial intelligence systems. And in this presentation, we are focusing on what are the human-centric digital twins. Here, a brief introduction about the context. So, despite the spread out of automation at the advent of Industry 4.0, the manufacturing industry is still characterized by heavy, non-ergonomic and tiring manual tasks. This is mainly due to the different capabilities that make humans almost irreplaceable in existing production systems. For example, capabilities like flexibility, creativity, problem solving, and decision making. And this key role will be covered also in the production system of the future. This is why Industry 5.0 brings back the human in the production system and is trying to, let's say, pairing humans with machines in order to increase the process efficiency, but also to improve the well-being of the worker. So before going into the details of the technologies that we are developing within STAR, I would like to provide an overview about the reason why we need technologies like human digital twins. In one of our recent research within our lab, we described a method to realize the paradigm that Industry 5.0 proposes. This way is characterized by what we call mutualistic and adaptive production system. With mutualistic, we mean a collaboration between humans and machines that increase both the well-being of the workers and the performance of the system. And with adaptive, we mean that automation systems have to be designed and deployed in order to be able to adapt their behavior based on the system conditions, but also on the workers' state and conditions and behaviors. This approach towards Industry 5.0 has been applied and validated in an experiment that you see in the video, where we collect physiological data from the worker and we try to estimate, thanks to artificial intelligence modules, the perceived fatigue exertion and the mental stress of the workers. we combine these features with the status of the system composed by a worker and a cobot, and in the status of the process, like the buffers levels, the quality, behavior, and so on. And we try to optimize the task assignment to the cobot or to the worker in order to optimize the process performance and the worker well-being. And in this experiment, I mean, it was quite successful since we achieved an improvement of the overall cycle time, but also of the quality and also of the well-being of the worker. So we find out a reduced fatigue of the worker and a reduced mental stress. One of the most relevant, let's say, challenge of this experiment was the digital representation of the worker. To achieve the improvement of the performance and the well-being, we had to model the worker as a data-driven agent to represent the interaction with the factory, but also to monitor his state. So at the time of the experiment, but also today, there isn't a standardized solution for creating human digital twins. So this forced us to let's say, to develop an ad hoc implementation and ad hoc models. However, this solution lacks of reusability, scalability, and extensibility, preventing the use, for example, in other contexts with other kind of artificial intelligence modules and so on. So the question is how to face with the challenge of representing the humans in the digital world, in particular to realize such kind of approach or paradigm, but also in other kind of applications. So the STAR project, as one answer to this question, we are trying to realize a digital twin or an infrastructure to design and implement human digital twins to create a digital representation of workers with the aim of monitor their well-being and safety, support the training, and improve the process performance. The vision is to realize solutions that are extensible and scalable, meaning that we are capable to apply this kind of solution in different applications, relying on different devices and systems, representing different features of the humans, but also of the things that surround the human. Interoperable, meaning that, I mean, we would like also to make it interoperable, meaning that the different solution and components, like the artificial intelligence modules, like the cobot or the automation system, have to be able to communicate each other. And finally, customizable, meaning that we are able to, let's say, to model different features, but depending on the application, we require a specific feature and others are not necessary. So we should be able to, let's say, to customize our solution and our model. So I forgot to switch the slide, I'm sorry. And what we are realizing between the main results of STAR, there is what we call the human digital twin core infrastructure. That is a solution that on one end support the creation of customized data representation of the production system and also of the human. On the other end, it is a modular infrastructure which allow to interchange the main components for the easily instantiate digital twins. You can see here in blue the elements from the core infrastructure that allow to, let's say, to collect, manage, and structure the data. For example, we are able to collect data from wearable sensors, but also from raspberries or from cobots. And then we make them available to the upper layer thanks to an Eclipse Mosquito broker. This is one example where we are currently, let's say, trying to manage also different kind of technologies like Kafka, like the Orion Context Broker. And then we have in green the functional modules that could be any kind of artificial intelligence module capable to elaborate, let's say, simple data time series in order to enrich the digital twin. The interoperability, let's say, the interoperability of all these components is realized mainly to the component that you see in orange, which is the orchestrator. this kind of, let's say, of components knows where the data how the data structure, where they are stored, how to retrieve, and so on. And it supports the, let's say, the interoperability between the different components and even also between the different artificial intelligence modules that we can integrate in this solution. For example, he also knows who are the workers in the system, which are the installed modules, the connected sensors, and so on. This solution is currently available on GitLab if you need to test it. We are trying to apply it in different validation scenarios, but we are also open to, let's say, to external application if you would like, also to apply human digital twins in your, let's say, in your industrial applications. The orchestrator mainly, let's say, the interoperability of the different components is supported by the orchestrator, but also thanks to this reference model on which the orchestrator relies on. It allows, let's say, to describe all the main entities belonging to a human digital twin, including human features, but also contextual elements. I don't want to spend a lot of time on this, let's say, on this model. If you want, we are publishing a paper at the CMS conference that they provide in more detail on the approach, on the infrastructure that we are developing, or in the paper that you see below, and also in the one of the deliverable that is public available on the STAR website. But what about the use cases of this infrastructure, and what about in general the use cases of a human digital twin? In particular, in STAR, we are following 4 use cases. The first one is similar to the one that I've introduced before. So the estimation of the fatigue. We stream physiological data from wearable devices worn by workers, and we collect them, we store them, and we are able to estimate the perceived fatigue of the worker thanks to a machine learning model. Another application that the STAR's core infrastructure supports is the, let's say, the worker characterization regarding the skills. So thanks to an adaptive GUI, we are able to collect the skills of the worker, and a module developed by one of the project partners, R2M, is able to, let's say, to compare the values provided by the worker with the ones provided by most reliable databases like ESCO and OSTARnet, in order to provide an assessment of the worker skill gap, and also to suggest some training paths. Another application and use case is the prediction of worker activity. In the same way as for the fatigue, we collect data from wearable devices, in particular accelerations. In this case, also we have a vision system, and this module developed by the FKI is capable to estimate the fatigue of, to estimate the activity of that the worker is performing. And finally, with Thales, we are trying, they are developing a module to optimize the AGV's path. So with a specific solution that they are developing to estimate the position of the worker, together with another module for the optimization of the AGVs, we would like to, let's say, to support the integration of this kind of modules in order to consider in the path optimization problem also the worker positions and the worker features. The first 2 experiments are already, let's say, in place and validated. The other 2 are still ongoing, and we are going to, let's say, to find out the different, to identify the possible way to integrate the different solution, to model the humans, and so on. I think that I have a small video, but I think that my time is over, so I give the floor to Jože for art related to active learning and explainable AI. If you have any question, please feel free to ask after the presentation. Thank you.
Thank you, Elias. Perhaps if you go to the next slide. Here in our case, we're focusing more on active learning and explainable AI. And the principles that we found that are important for our use cases are that we see that the humans and machines have different capabilities, and so we can learn from each other. Like the kind of intelligence that the machines and the humans display is different. So what we can see is that the machines perhaps can analyze multiple data sources and find different patterns that are not that intuitive to the humans. But at the same time, they cannot learn from the data that they have if we don't teach them how, and also in some cases, if we don't structure the data in a proper way. What we see is that when you have this kind of complementary capabilities, also you can speak about synergy, because what we're trying to do is to build on top of the capabilities and strengths that each of them have, in order that we can create some results that supersede the individual efforts of each of them combined. And finally, like the project STAR that we are working on is all about how we can develop artificial intelligence that is human-centric, and also that we can trust it and make it safe for the humans. So developing a component where we can foster this kind of mutual learning and synergies also creates like a place where we can develop the trust from humans into machines. Here what we see on the right side is in some way like a flow that tries to depict how we combine active learning with explainable artificial intelligence. Usually what we have in active learning is a machine learning model, artificial intelligence model, that has certain certainty for most of the use cases, for most of the cases that are presented to them to issue some forecast. But for some of them, they perhaps don't have enough confidence. And for those cases, we request the input from a human so that they can provide data regarding that, and the machine learning model can learn more about it. Usually, the assumption here it is that we have abundant data, and we need somehow not to just provide a lot of data to the machine learning model or the artificial intelligence model, but we can select which data can be most meaningful to the model so that they can learn most of it, and then based on that also improve their performance. But doing accurate forecasts is not the only thing that is important in these cases. If we would like these kind of systems to enable responsible decision making, we also need to understand why is forecasting certain prediction. So we need to get some kind of explanations to understand the rationale beneath the machine learning model. And that is what we provide through explainable artificial intelligence, through different techniques, and also perhaps using transparent models that give us that kind of capabilities, so that the user having the forecast and the rationale behind it can then make better informed decisions, and also decisions in a responsible way. If we can go to the next slide. So here the main question that is driving our research is how we can develop synergic relationships within humans and machines so that we can learn from each other, leverage each other's strengths, and then build trust based on that. If we go to the next one. As mentioned before, in active learning, what we are trying to do is to automate what it is possible through machine learning models, so that we can reduce what is the monotonous work currently performed by operators, and then use their time to focus more on creative tasks. We would like to the human not perform things that can be easily automated, but really where their intelligence and their creativity is required, and where they provide most value to the enterprises. We can see that the machine learning models are not perfect. So what we would like to do is some way to create a human in the loop synergies where we can help the models learn where they are most uncertain about. And we can either select interesting data for the model, or either perhaps also create synthetic data instances. Sometimes creating this kind of synthetic data instances can be cheaper, and it can be created with two purposes. One is to feed the model, especially if we have very rare instances that is difficult to get them in the real world setting. And otherwise also can be if, for example, as will be shown later, we have a defect detection scenario. If we are getting like most of the stream with good cases, but some of them just defects, it is very easy that the humans may overlook those defective cases. So what we would like to do is to generate synthetic images to balance those kind of streams, and then also prompt the attention from the users to the images that they are getting, enhance their attention, and enhance the quality of labeling at the end. So what we would like to do in some kind of active learning is not focus on more data, but focus on less data. But always with that kind of data that they are selecting, the data instances should provide like more quality to the data set. And also, as mentioned before, we can generate data. And then we can also consider this kind of active learning in a broader sense that is not traditionally considered in artificial intelligence just as this kind of instance selection so that you get the most informative or the best instances following certain criteria to improve the model. But also we can say if we have some certain knowledge graph, we would like to analyze what kind of data is structured in the knowledge graph. We can follow some heuristics to understand perhaps what kind of data we are missing given a certain context, and then develop means so that we can ask the user to complete the missing data or things that perhaps we don't understand about or the model does not understand about, so that we can encode iteratively that kind of locally observed collective knowledge that is not present in the knowledge base, but should be, and like the larger that knowledge base grows, better is the product and assistance that we can provide to humans through these kind of machine learning models and knowledge graph models as well. If we go to the next slide. Regarding explainable artificial intelligence, what we can do is like we try to provide some kind of explanations and insights regarding this kind of models rationality behind the forecast, as mentioned before, so that the human can then decide if can trust or not trust the specific forecasts that are coming from our models. What we see is that these kind of research methods can provide skills not only to data scientists who are developing these kind of models, but also they can be helpful to the end users who are taking the decisions. And the way these kind of insights are provided to each of them should be provided in a different way. Perhaps regarding on the how well you understand the inner workings of the model, how much exposure do you get to the different features. For example, for people who are not technical, they are not interested in the specifics how the features are defined, but perhaps more on the overall concepts that are guiding that kind of forecast. So we need to create different abstractions so that this kind of information is presented in the right way to each of them. Also, usually it is a good practice to make this kind of feature, this kind of insights actionable, so that they can relate directly to the user on how their action either to change the forecast or perhaps how their decisions may affect the future outcomes. Another interesting insight is also to understand, like all together with this kind of insights, is to provide complementary information so that we can help either or enhance the model or either enhance the understanding of what is at stake when making a certain decision. And also we need to study how these kind of decisions that are provided, these kind of insights that are provided to the user are understandable, are intelligible by the users, or if we are providing some information that is not useful at all. So we have a different branch studying also how this information should be conveyed so that the user understands well and can make, can learn on top of it, can make good decisions on top of it. If we get to the next slide. So what we try to do is in some way to combine this active learning and explainable AI in a specific use case that is about Philips. We have a branch of Philips in the Netherlands. They are working close to us for this use case. What we are trying to do is to automate visual inspection, creating highly accurate models that try to discern if there is a defect or not in the product that was manufactured. And also what we try to do is to create this process in such a way that we have a human in the loop so that we foster this kind of human learning we were talking about before, and then also foster this kind of synergies and trust based on the explanations that we can provide regarding the forecasts that were given to the user. In this work that we are evolving with our Philips partners, we received an initial level dataset with shaver images, and then we are conducting also on-site experiments with different operators. If we go to the next slide. Here, what we can see in the left side are images that depict what is a good case and two kinds of defects that they have, a double printing and an interrupted print. Perhaps the interrupted prints are the most difficult to spot because even if this case is pretty obvious, For example, in what we see in the left side at the bottom, we have also an interrupted print, but where it is not that evident where the spot of the interruption it is. So what we have is machine learning models that try to detect that, and we also experimented with some kind of strategies or means to give cues to the users, so that by presenting what a good sample should be, the current piece that they are inspecting, and possible cues on where the defect may lie, we can do several things. We can inform them how the model is thinking about where the defect may lie. Also, we focus the attention of the user who is performing the inspection just on the parts that we think that there is a defect on. So they don't need to scan the whole image and perhaps lose precious time on spotting where the defect may exist, but just focus on where we provide the cues that this kind of defect may exist. And also with this, what we would like to do is to reduce the labeling time over time, and also use complementary strategies so that we always ensure that the people don't get tired, and perhaps also monitor their fatigue when doing this kind of labeling. In active learning, again, what we see is that by creating these machine learning models, most of the load is no longer posed on the workers for doing this kind of visual inspection of the defects, but is completely automated. And just we focus on this kind of labeling for the cases where the model is most uncertain about, to ensure that we meet the quality, but at the same time reduce the manual workload and speed up the process. If we go to the next slide. And some future work we'd like to focus on is perhaps how to ease this kind of manual revision we were mentioning before. We are doing more research on this kind of defect hints. What we explore are different techniques. We would like to explore even more of them, so that we see what is intuitive and not intuitive to the user, and what also helps them to increase their speed and accuracy when labeling. For now, what we have achieved is at least 30% of increase in speed in this labeling while retaining a very good accuracy. Also, what we would like to understand is also if there is certain context that we are not aware of and that is meaningful to the operations of this kind of inspection. So we would like to gather this kind of information from the users and enrich our knowledge base with the contextual information that is meaningful, and also to detect this kind of workers' fatigue, as mentioned before, when they are performing this kind of labeling. And what the preliminary results show that we can detect the phases when this is happening. So now we are experimenting on how we can apply machine learning algorithms so that we can smartly suggest them, for example, breaks or other or follow other strategies that can help them to reduce this kind of fatigue, and then also increase their speed and labeling accuracy when dealing with this kind of data. And perhaps if we go to the next slide, I think with this we have finished and we are able to take questions.
Thank you very much, Jože. So let's see if we have any other questions. We are a little bit over time, but I think it was interesting to have the discussion. I think there are some questions earlier, in the chat about the presentation, about how difficult it is to develop a human digital twin if you want to start by, recognizing gestures and human context or other signals. So these are, questions before in the chat, but anyone feel free to take the floor and ask any questions on this last presentation.
Hello. I'd like to ask you about contrastive explanations. You only talk about abductive explanations. Are able to process it also? Thank you.
Sorry, if we are able to process it?
Constructive explanations. The question is, you are talking about the why questions. I'm talking if you are able to process also why not questions.
No, we currently focus on that.
Okay. And you are able to understand models from which kind of classifiers?
Sorry, if we are able to understand which kind of classifiers.
Classifiers. Which are the classifiers you are able to answer to why questions?
Yes, we developed like multiple classifiers, and we are using different approaches in order to provide this kind of insights regarding where it is happening. Like you have some of them that are like deep learning techniques, some others are follow like different approaches, but for each of them we are able to provide this kind of insights regarding where the model is focusing on, so that they understand or where they think that the effect is, so that we can present it to the user. The techniques depend depending on the classifiers that we develop. But we won't go into the details regarding the specific features that we are using, the specific classifiers we developed for each of those cases.
Okay, thank you.
I will have one question. Have you been able to see that when you apply your technology to some manual work, that the worker who has been exchanged with the machine or with the technology has been given a creative work? Because you mentioned it that they will be released to make a creative work.
Yes, that is right. Currently, we are still in the experimentation phase where like what we try to do is to automate this so that the users can focus on more high-level work. What we have is for this quality inspection, still the changes have not yet been done in the factory so that this is implemented. But what you expect is that like the workers will be doing will be relocated to some kind of different work or a different assignment, so they can focus like on really more creative work and not this kind of manual inspection that's being done right now. So just that.
I just would like to recommend that you support the company, the employer, even in the right setup of the relocation. Because usually if the workers, the manual workers get relocated, they get even worse work, which generally is not able a machine to do, like carrying something or picking something or whatever, but it's not a creative work. But I think you, because you collect a lot of data, that these data can be used for even improving the HR in setting up a better environment for the workers, which is not the case generally, but it will be very interesting if first company does this as a part of the package which you do, because you collect data. Don't waste this data just for one solution, but use it as much as possible. That's just a small recommendation.
We agree on that. We are sure that Philips does what is best in the interest of their employees. So that this will be done so that they really do something that is interesting. We still did not get to a phase where we can research like other approaches. We are just trying to finalize for this phase. And then when this is done, we'll go over iterating how we can provide more value and also things that are more interesting to the users. Like for now, we are trying to solve this specific use case, and then we'll iterate further. But thank you always for the recommendations.
Thank you.
Maybe I can answer to Cosmas, which asked about the, let's say, mutual communication between the digital twin and the human. For example, in the experiment that I showed before, the system communicates to the human, which are the tasks that the worker has to perform, because we have mutually executable tasks. So tasks that can be performed by both the cobot and the human. So depending on the status of the fatigue level and the mental self of the worker, and depending on the process conditions, we decide which task the worker has to perform and which task the cobot has to perform. This is one of the, let's say, the communication that happens in the system. On the way around, the worker also can, let's say I need to rest. So the system knows this need from the worker, and we implement, let's say, a work cell configuration that allows to to work without the worker. I mean, as far as the process allows to do that. Hope that I answered to your question, Cosmos.
I have to ask all of you, all of the speakers, because I am not AI expert, not at all. I do not have academic education. Have you been able to teach AI to do imperfect work, not perfect one, but the imperfect? Why I'm asking, because the imperfection is a human ability generally, and imperfection, it's nature. But nature is here for millions of years. Revolutions and machines are here just for short time. So there is something about imperfection. And my question is there anyone who is touching the topic of imperfection in AI war, or is just a crazy idea of Mr. Rada?
Well, I think the point is to use the technology to avoid the mistakes of the human, right? At least this is what I understand. I don't know if there are any other ideas. Maybe I don't know if you want to say something on this, Elias, and then we can close the meeting as we are already 20 minutes late. I think also the chat is recorded, and there are very nice ideas in the chat already. So I don't know, Elias, if you have any comment on this, and then we can, or Jože, of course, and then we can,
I mean, honestly,
close the meeting.
Okay, I'm also not an expert on artificial intelligence, but as far as I know, it's really difficult to have also perfection in artificial intelligence. So the error is, I don't want to say intrinsic, but we also expect errors and we do not expect perfection in artificial intelligence. But of course, I mean, it's not, depends why we would like to have this imperfection. Is if the reason is to mimic the worker behavior, it has sense to have this imperfection, since for example, we want to emulate the behavior of a worker. As you said, humans are characterized by this imperfection, but otherwise, why do we need imperfection in automation systems? I mean, we would like to avoid such kind of.
It is interesting because if I go back to the digital twins history, generally you have to copy the factory, including all the imperfections, because only so you will be able to copy the real environment. If you do a perfect double twin of operation which is imperfect, the digital twin will not work. It will not deliver the real results. So this is why I'm asking generally. But thank you for the reply. I do understand what you mean, and thank you for the reply. I do not want to take.
Yeah, maybe one last thing. The point is that how can we include in the simulations or in the predictions the unexpected event? This is quite or something that we do not expect for example, from an automation system, and so this is quite complex. And honestly, I have not a complete answer. Thank you for the question and the discussion.
Okay. Thank you all for being here. Thanks for the live discussion. It's good that all these workshops, also the previous ones, had a very interactive discussion, and it is a pity that we didn't account for even more time. And thanks very much for the speakers for all these presentations. So we will make the PDFs available in the cluster webpage. And we will email all registered participants. And we hope to see you in the in one of the coming webinars as well. So thank you very much. Paolo, maybe we can stop the recording.
Yes,
and,
thank you.
Conclude this webinar.
Thank you, and bye-bye to everybody.